Okay, so today I'm going to talk about anti-aliasing, and I have some handouts because this stuff isn't in the book. On the last page are possible suggestions, possible topics for your final projects. And, can we start? I forgot to do the thumbs up thing. We're going? I emailed these documents to the students at Livermore, so you can get them that way instead of through the instructional TV like I've been doing earlier. So the idea is the section in the book talks about using a filter function, H they call it, for integrating over the pixel area. It might actually be wider than the pixel area. And the way to understand it from the point of view of signal processing is using Fourier transforms. How many people know what a Fourier transform is? A few. So some of you have had signal processing application. How many people know it in the context of signal processing? A few of them. Okay, so it's repeat for those of you. And it's new for most people, I guess. So what we're going to do is if we have any function, I say f of u, where u is a real parameter, actually it could be, f might be complex because the Fourier transform, which is written capital F, let's say f is a function of x. And the Fourier transform will be a function of frequencies. It's like when you see audio analyzers and they have like bars coming up for the energy in the different parts of the frequency spectrum. That's frequency as a function of time. We're going to talk about frequency as a function eventually of space with two parameters, but it's easier to understand in terms of one parameter. And so this is the integral from minus infinity to infinity of f of x e to the minus 2 pi I u x dx. So this frequency comes here, and since e to the minus 2 pi I u x, e to the I anything is cosine of that thing. The thing that multiplies I is 2 pi ux plus I times the sine of 2 pi ux. So basically, you can think of the real part of this Fourier transform is the integral with the cosine. So if you have some frequency exactly the same, that integral would sort of be infinite, a delta function. And otherwise, it would probably be zero because the frequencies would beat against each other. And when you did the integral, the positive parts would cancel out with the negative parts. Let's see. So that means f of u is the integral with the cosine, 2 pi ux, plus I times the integral with the sine. Okay, and now you can get an inverse Fourier transform to go backwards. And let's see, I had a minus here, so this should be minus. Right? If you have minus an angle, the cosine is the same, but the sine is minus. So this should be minus. And for the inverse transform, we get back from f of x by doing the same kind of integral, only with a plus sign. So that plus sign or minus sign doesn't make any difference with the cosine term, only for the sine term. And let's see, let me just keep up with the different things. The delta function or the impulse function has the property you can think of it as delta x equals 0 if x is not equal to 0, and some sort of infinite thing if x equals 0. But how infinite? Exactly, the definition really says that if you integrate it with respect to any function, delta x minus u then is going to be 0 unless x equals u, and otherwise it's going to be infinite. But the real thing is it's just infinite enough to make this come back to be f of x, the one place where this quantity isn't 0. So basically its integral should add up to 1, even though it's non-zero only at a finite, at one point. You think of it as sort of a limit of steeper and steeper, narrower and narrower bumps. Okay, so I need one more definition, which is the convolution of two functions, say f of x and g of x, and it's written fx with a star g of x. And what it is, let me write it over here, f of x star g of x is the integral from minus infinity to infinity of f of u g of x minus u du. So it's a new function of x because we've integrated out the u. And it's convolutions that we're going to use for filtering an image. If we think of a symmetric g of u, in the book it's h of u, some sort of a bump function that is concentrated near 0 and sort of blurs the image out. If we multiply this, say at x equals 0 by this, it'll integrate a bunch of different values of x. Say x looks like this. Here's f of x. It'll be a weighted average of f of x, the values near 0. And then if we move the filter this way, it'll be a weighted average of these values. It sort of smooths the function out. You know, it'll sort of blur this peak, and the weighted average will be some sort of thing like that instead of something with a corner. And we'll see that that's the kind of thing that gives better anti-aliased images. So, let's see, let me do these facts. If you have s of x, this should have been a lowercase s, maybe I'll write it like that, is the sum I equals minus infinity to infinity of delta of, I guess it should be j because I've got a j in the notes, of x minus j delta x. What that means is you have a function, a spike at 0, and then for every spacing delta x, you have spikes here. So it's a train of spikes. And the application we're going to have is if you have a sampled image, it's as if you multiplied it by this spike of delta functions, series of delta function spikes, and think of you only sampling it at these exact positions and forgetting what it is everywhere else. And then the idea is S of u, the Fourier transform, is also a similar sum. I guess I have k there. K equals minus infinity to infinity. So we have another bunch of spikes, but the spacing of those spikes is 1 over delta x. So how should I write that? That sum is u delta u minus k over delta x. So the spacing instead of delta x is 1 over delta x. And the idea is the Fourier transform of this thing equals that thing. Sometimes people write it sort of a script f. Fourier transform of s of x equals capital S of u. And suppose we take a Fourier transform of a function which is like that. So here is x, and here is f of x, and x is going, and this thing is going to have height 1 here, and then go to 0 at minus x minus, what do I have? Capital X. Capital X is the width of the pulse. So from here to here is capital X. So this is minus capital X over 2. And this is plus capital X over 2. And that means f of x is 1 if minus capital X over 2 is less than or equal to lowercase s is less than or equal to capital X over 2, and 0 otherwise. So this time I can actually compute f of x, because that's supposed to be the integral from minus infinity to infinity of f of x e to the minus 2 pi I u x dx. Then that's capital F of u, frequency u. Okay, and now from the other board, well, first of all, because f of x is 0, except for in between here, we can replace that by the integral from minus x over 2 up to capital X over 2. And then f of x is 1 there, and then we can just have the cosine 2 pi ux du, and a similar integral minus x, capital X over 2 to plus capital X over 2 with an I in front of it, and I guess I have a minus. That's the same mistake I made last time. Sine 2 pi ux dx. And this one is going to be 0, because sine is an odd function. It's negative here and positive there. But cosine is an even function. And so we're actually going to get something for that integral. And basically what I have to do is find out what is the function whose derivative is cosine 2 pi ux. And I guess the derivative of the sine, if I take d du of sine 2 pi ux, I'm going to get the cosine 2 pi ux times the derivative of this with respect to x, which is 2 pi u. Okay, so that means this integral from minus x over 2 to x over 2 of cosine 2 pi ux, what I'm going to have to do is take sine 2 pi ux and divide it by 2 pi u. This was dx, and now I'm evaluating this, which is the antiderivative of that, just by dividing both sides of this equation by 2 pi u, between minus x over 2 and plus x over 2. And so I have, let's see, sine, at the upper limit, I have putting for the x here, capital X over 2, this 2 is going to cancel that 2, and I'm going to have 2 pi. No, I said that cancels. I don't have the 2 pi. Just pi u over 2 pi u. And then I have minus at the lower limit. And at the lower limit, I have a sine of a negative angle, minus x over 2. And that's minus the sine of, if it were positive, which was pi u. over 2 pi u. So these minuses cancel, and I have a plus, and then I have 2 of these, and that cancels 2 in the denominator, and this is 2 sine, I'm sorry, not 2, sine pi u over pi u. And sometimes people say S-I-N-C. I don't know how they pronounce it. Maybe sinc of u. So this is a function which, where can I draw a picture of it? Maybe over on the first board. It's a function which is 1 at pi equals 1. I mean at 0. Why is that? Because it's 0 divided by 0, and you have to use L'Hopital's rule. The derivative of the denominator is pi, and the derivative of the numerator is also pi. So by L'Hopital's rule, it's 1 there. And then at every other multiple of pi, it's 0. And in between, it sort of has wiggles. It comes down here, because nail sign is negative, nail sign is positive, but the denominator is bigger at every step, so these wiggles are less and less as you go out. So this is sine pi u over pi u. So that's the graph of that function, which is the Fourier transform of, let's see, I forgot my x, right? You didn't catch my, I put x over 2, and I said the 2 cancels that 2, but I left out the x's. So everywhere here I have an x, here I have an x, here I have an x, and I plotted it as if x equals 1. So basically, where it becomes 0 is at u equals 1 over x, because that's multiples of pi. So this spacing is 1 over capital X. So the narrower I make that window, the wider this gets, and vice versa. So sorry for the typo. Okay, so looks like I need to show you the convolution theorem now, which I'm not going to prove. Well, maybe I can. The proof is in the sheets, but it's getting late. So look on the sheets for the proof. It's a formal proof anyway without the limits there. F of x convolved with g of x. If you take the Fourier transform of that, it's just the product of the Fourier transform of the first one times the Fourier transform of the second one. So we can say that's the product of the capital F of, probably I should put a U in here. And similarly, the Fourier transform of a product equals the convolution of the Fourier transforms, F of u convolved with g of u. So let's see, which one of these did I actually prove here? I guess I proved the first one. And if you're following on the sheets, you can just follow that proof when you get home. So what's this good for? The main thing I want is the Shannon. I usually knew it by just Shannon's sampling theorem, but I guess there was a simultaneous author at some point. Whittaker sampling theorem. That says if f of x has no components of frequency, say greater than w, which means when you take its Fourier transform, the Fourier transform is 0, except between minus w and plus w, because the Fourier transform represents those frequencies. So that means capital F, i.e. capital F equals 0 if absolute value of u is greater than this w, which is the frequency limit. I don't know why this part isn't erasing. Then f of x can be reconstructed from discrete samples at spacing delta x when that should be an E, V, E, R. Delta x is less than 1 over 2w. So let's think in practice of sampling some picket fence. Usually they illustrate it in terms of sampling a sine curve. Either way, but oops, this isn't erasing either. I think something is wrong with either the chalk or the blackboard, but let me think of a signal which is like a picket fence. Up and 0 and up and 0, up and 0 and up and 0. And this actually has infinite frequencies because of these sharp things, but I can still illustrate the idea of aliasing with it. If I sample here, 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 I'm going to get white, black, white, black, white, black, and I can sort of reconstruct those vertical stripes of the picket fence. Say this was a function of x, and in terms of y, it was the same thing. I just had these vertical stripes, and I'm thinking, what do I see on a scan line? But if I sample it slightly slower, then what I might get, suppose I sample it twice as slow. I'm just going to get pure white. And if I sample it somewhere in between, say here, 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 I'm going to get 2 blacks, and then a white, and then probably 2 blacks, and the next white. I'm going to get something that has actually got these whites every other time. And so basically this high frequency is aliasing at a lower frequency. We call this, so then the signal that you'd reconstruct, if you sort of average this out and made blocks of it, is going to be something like that. Right, so it's as if this frequency aliased as another frequency. Alias is like a fake name or fake appearance. And that's called aliasing. And you can actually show mathematically that if you take a sine curve and sample it at the wrong frequency, it'll alias as another sine curve that has, if you alias it a little bit, if you sample it a little bit too slow with respect to this threshold, you'll end up with a very low frequency, basically. So what we want to do in computer graphics, we want to do anti-aliasing. We want to avoid the aliasing. And what this says is if we can sample it finely enough, we could avoid that. And finely enough means according to the highest frequencies. So what we'll have to do is we'll have to filter the function before we sample to remove those high frequencies. And to filter it, we want to multiply the frequency spectrum by something which wipes out the high frequencies. And by the convolution theorem, that multiplication corresponds to convolving the signal with a filter. So let me illustrate it by the pictures on this sheet, these sheets. And let me say, if this is the first time you've seen this, it's going by very quickly. But at least you'll have heard the words, and you'll probably see it again and again in computer graphics in the context of anti-aliasing and sampling. But suppose we have a function here. This is our original function f of x. And it has a certain Fourier transform which goes from minus w to w. This just says the frequencies in this signal have this range. And now we're going to sample it, which means we're going to just compare the function. I didn't draw the same looking function, but assuming I could, we're going to, that looks better, we're going to take these discrete values of it, which is like taking a single ray at the center of a pixel and figuring out what color it is, like you did for the first assignment. And this spacing is going to be spacing delta x. I guess it's delta, yeah, okay. And then that means the Fourier transform of that has spacing 1 over delta x. So this spacing is 1 over delta x. And if delta x isn't small enough, these will be too close together. And now the sampling is really the product of these train of delta functions times this function f of x. So by the convolution theorem, the Fourier transform of that will be the Fourier transform of the, which is this spike train, convolved with this. And basically the convolution of these delta functions is going to pick out, like this delta function is going to just pick out the exact value of this function here. So that is going to look something like this. But this delta function is going to pick out a shifted version of this. So we have multiple copies of this frequency spectrum. And in fact, this copy as it comes in is sort of what gave us the aliasing. It's not part of the original frequency spectrum. It's another frequency that's aliasing here because it's in this shifted copy. And we want to get rid of that. And one thing we could do is sample more finely. So here's my function f of x. And if I sample it more finely, then I'm going to get these spaces will be farther apart, and there'll be room for these things not to overlap. Well, once I get it so that they don't overlap, then I can just pick out the middle one. And by picking out the middle one, basically what I'm going to do is I'm going to multiply this picture by a filter which goes from minus w to w. Right, so I have all these other copies. But when I multiply these, I'm just picking out the middle copy. Well, by multiplying here, what I have to do is let's see, multiplication, I do have to do the convolution. So it's the convolution of the original function f of x. I'm sorry, it's the convolution of my function here, which was these sampled things, times a sinc function. So the sinc function is the function, like for this sample, I'm multiplying it by something that goes like that. And for this sample, I'm multiplying it by something that goes like that. So basically, I'm getting the same values at each of these samples, but I'm putting something smooth in between, which will reconstruct my original f. So that says that over here, you can think of, let's see, do I want to have, this is my f of x, this is my capital F of x. Here is my sample. And this thing was, these spikes were the s of x, and the convolution, capital X, convolved with capital F of x. And now I have this window function, which they call g of u. And I took g of u times the product f of u convolved with s of u. And then here I have the inverse Fourier transform of that, which was the convolution, lowercase g of u, which is now my sinc function, convolved with the sampled f of u times the train of delta functions, s of x, s of x. This should have been x here. That's u there. And so this is perfect reconstruction, assuming that you don't have the high frequencies. But suppose you do have the high frequencies, right? Suppose you decide on your sampling rate, and your sampling rate is like this, just once per pixel. You're only going to get one number per pixel out of it. So what you want to do to get rid of aliasing is you want to say, let's take these overlapping things and chop them, right? So that, well, basically what we have to do is we have to chop this, right? So it's 0 here. Throw this part away, right? So to throw that part away, we have to multiply f of x times multiplied by, let's see, what am I going to call it here? Maybe h of u, where h of u is something which goes from, say, minus 1 over 2 delta x to 1 over 2 delta x. So its width is the spacing of these copies. Okay, so to do that, what I have to do is I have to convolve my original, maybe I'll put it over here. So this is a sampling filter. The one I was doing here is a reconstruction filter. From these samples, how do I reconstruct the original signal? But what I want to do here now is I want to, here, maybe I should, here, let's leave this guy here and draw this one here. So here's the one that I've chopped off at this width. 1 over 2 delta x. And so this is my f of u, and this is capital F of u multiplied by h of u. So now I have to do a convolution here, f of x convolved with h of x, and this window function that I'm multiplying it by, here is my h of u, which is is this, again, it's a square window, and for symmetric things, the plus and minus for the I is only for the sine terms, and we've made a symmetric thing with respect to 0. It's an even function, so it'll only have cosine terms, because you integrate the even with all. So it doesn't matter. The inverse Fourier transform and the Fourier transform are the same thing. So that means what we have to use here is this sinc of, I guess it's delta x u. And so that's a function that here is delta x, the spacing, and what we have to do is we have to multiply this function by a function like that and integrate to get the value of this convolution. And at another x, we have to do another one. And then we can sample it. After we sample it, we're taking this thing and multiplying it by this sampling function. And what we'll get is just copies of this, which don't overlap. So then when we go through this process of the reconstruction filter, we'll get back not the original function, but the smoothed out function. So the smoothed out function may remove frequencies. Like if the original function had some sharp jumps in it, when we convolve with this sinc function, that's going to wipe out the sharp jumps. And we'll get a smoother function which doesn't have those high frequencies. And then we'll know that we can sample it, and then we'll get all the information in the function. So to do that, ideally, to reconstruct the function, you'd have to use this sinc function as a reconstruction filter also. So there's pre-sampling filter to blur out the function so that it doesn't have frequencies which will alias. And then once you do that, then the reconstruction filter is the thing that removes these extra copies by smoothing out the result of these samples here. So reconstruction filtering has to do with how you display on a screen, especially if you magnify it a lot. And that's not really so important for us. We don't really necessarily have control over that unless we're writing an image magnification program. But we can do the pre-sampling filter. So ideally, the pre-sampling filter is also this sinc function. Let me go back over here. Let me assume x is 1. So we're sampling by pixel spacings. We're measuring in units of pixels. And then all our frequencies would be spatial frequency per pixel. So an ideal filter would be to multiply the function by this. Now, it's manageable because we only need to get the values when we're sampling at specific points. We don't have to reconstruct for a continuous variable what this convolution is. But we do, for each sample, have to convolve the whole function f of x, whatever it is, by this filter. And this filter has got negative weights as well as positive weights, and it goes all the way to infinity. So we already saw that if we just, instead of multiplying it by a filter, we multiply it by delta function, we can get really bad aliasing. But suppose instead we multiply it by a square window. In other words, you take everything that's closer to this pixel than that pixel. So you're multiplying it by a window like that. How does that compare to the ideal filtering? Well, first of all, you're still going to get some aliasing. You're still going to have some frequencies outside of the window of spacing delta x here. And that's going to give you some aliasing, but not as bad as just sampling in the middle. Because this is like the pixel average. And if we do this in x and y, it's like saying, here we have the pixel square, and we're going to integrate over the area of the pixel square with constant weight, and also in y. That corresponds to a pixel like this. And you have some aliasing and some blurring here. Because frequencies near this cutoff are actually, how can I say it now? What do I want to say? my ideal filter is both a reconstruction filter and sampling filter, and it's also this sinc function in 1D is, if I take the Fourier transform of this window, what I'm going to get is a sinc function. Maybe I should have been saying it that way. Here's my sinc function. So it's 0 here, and 1 here. This is the Fourier transform of this square window. And now, if we look at the ideal filter, frequency filter, and so the ideal frequency filter has this sinc function to be integrated by, and instead we just want to integrate, you know, everything from minus a half to plus a half. If this is pixels, this is 1 over 2x. It should be a half and minus a half. That corresponds to a filter. So this is the Fourier transform of the box filter. That corresponds to the integral I did before. And so this is the picture where I should say that this amount of falling off in the capturing of frequencies before the cutoff is blurring, and this part here where it's non-zero, where, you know, it's keeping frequencies that should be thrown away outside this frequency cutoff. This is the can cause aliasing. But it's not as bad as just sampling in the center of the pixel. Just sampling in the center of the pixel would just get this bunch of spikes, which has aliasing all over the place. But you can do better than that. And one thing people do, so this is, what do I call it? This is space, and this is spatial frequencies. Suppose you take the convolution of this square with itself. Right? So if I think about it, I have this square, and now I want to take a moving filter where I multiply the two of these and integrate. What you're going to see is it's going to go increase linearly until they just overlap, and then it's going to decrease linearly until it goes to 0. So the idea of that is, in this, if I draw a picture of it spatially, it's a triangle filter. Right? So basically, in terms of computer graphics, as if you make the pixel window twice as big. Here are our pixel samples. And instead of taking the square from like I minus a half to I plus a half and so on for j and just integrating it over, we're going to take this bigger square, twice as big, and we're going to integrate with respect to a triangle in x and a triangle in y. It's a sort of a tent that goes down in both directions. So this filter basically in two directions is h of, what do I call it? hij of x, y is the absolute value, well, why don't I say it's the same as hi of x times hj of y, and hi of x equals, let's see, it's got to linearly increase up to 0. So it's this third. 0 if the absolute value of x is greater than 1, actually greater than or equal to, and my triangle from minus 1 up to 0, it's increasing. So it's going to be what? It's going to be x minus 1. Let's see if that works. X minus No, it's x plus 1 if minus 1 is less than or equal to x is less than 0, because if I add 1 to a minus 1, I'll get 0, and if I add a 1 to a 0, I'll get 1. And it's the other way around. If 0 less than or equal to x less than or equal to 1, what does it have to be? It's got to be 1 minus x to decrease to 0 as x goes from 0 to 1. So there is a triangle filter, and I just said that that's the convolution of two square filters. And so what that means is that its filter, why don't I say the Fourier transform of this, I don't know, why don't we call this, what did I call it? What did I say it was? It was box filter, maybe. Box filter times box filter. Convoluted with box filter is the Fourier transform b of x multiplied by b of x. And the Fourier transform of the box filter is this sinc function. So if I take the square of the sinc function, I'm going to have something that decreases more rapidly here, is 0 here, and is smaller. Basically, it decreases to 0 more rapidly. It has less aliasing. It still has some. It has more blurring, but less aliasing. So what I did on the next to last page of these sheets is I tried to see what would happen if you did point sampling. Yeah, I think I'm going to have to do this next time. There's no way I'm going to get through all these cases today. Just like how using a triangle filter improves things. But what I can do today is say you can go one step further. You can convolve this with itself. Yep, this box filter one more time, and you'll get, you think about something moving across here, it's increasing quadratically. Let's see, from here to here, it's increasing quadratically. Once it gets to here, it doesn't increase as fast and actually starts decreasing when it comes here. Let's see, is that right? Now this is the, let's see, how do I make my square? My square was this width. So it increases when it gets right in the middle, it's the maximum. And then when it moves to here, it decreases again. And it's really made up of 3 quadratic segments. One quadratic segment when it's just making this triangle bigger. And that's a quadratic segment like this. And then another quadratic segment when you're starting to get part of this other part. And that's going to be a quadratic segment like that. And then another quadratic segment where the box filter is only overlapping the right-hand part of the triangle. And the width gets to be, you know, even bigger here. It's halfway to the next row of pixels. And it's basically the cube of this box filter. And now it's going to be, the convolution 3 times with the box filter, because twice gave the triangle. And then if you take this b cubed, then you'll make a filter which is even less aliasing and more blurring. And you can see already this shape looks sort of like a Gaussian. So that, you know, some people use piecewise quadratic or piecewise cubic filters, get closer and closer to something like a Gaussian. It turns out that the Fourier transform of a Gaussian is another Gaussian. And what I should say, an advantage of the quadratic thing is, well, let's see. This one I drew it wrong, right? Because I drew it negative. It's actually the square of a positive thing, even a negative thing is positive. So all the bumps on this thing squared are positive. And when it's cubed, the bumps get even lower, although some of them are negative again. So it just goes like that. So what I want to do next time is look at some of the things in this table about how the square filter and the triangle filter and the point sampling result with sort of images like bars or picket fences or thin lines or whatever. So that's it for today.